by stretching it, bending it, but I can't tear it apart or I can't glue it, right? If the shapes remain, if the properties of that particular shape is conserved, then I would say that those two shapes are topologically equivalent. In simple language, if I say that a particular, for example, say square as well as circle, then I would say that in R2 they are both homomorphic to each other. That means that square is homomorphic to circle or square is exactly a circle. I will come to that point and show you how. Right. So what we do in topology, we check the properties of the shapes. Does it remain? Is it conserved or not conserved when I change the shape of that object by stretching, bending? Alright. So that is what we do in topology. Getting what I am trying to say is? Getting what I am trying to say? Okay. Next one, it is a study of geometrical objects without considering things like length or I said earlier that in geometry we study all the aspects of that shape, right? But in topology we will only consider the properties which are conserved or not when I change the shape by bending or doing, but not tearing, right? So it is a study of geometrical objects without considering things like length, angles or shape. It's a very good thing because it can be applied to a very big, it has a big application. I will tell you that example. Then next is the coffee cup can be transformed into a donut. Everybody knows what is donut. Like mascarpone. It has a shape like mascarpone. A coffee cup can be transformed into a donut by stretching and twisting. However, a ball can't be turned into a donut without tearing or cutting. I will show you how. This is a coffee cup. It was a cup of coffee, right? So now, alright. Without breaking or tearing, there was an animation which transformed cup of coffee into a donut. Alright. There is one more particular word for the donut. The shape is known as torus. Alright. Now, actually, we are learning topology since we are kids. Kids in our diaper days. How? Let us see. Taking off a vest without taking off a coat. How? What we need to check is that the object should not be teared apart. Alright. If we can then modify its properties, then the both will be totally the same thing. What she will do is, she has wore a black jacket, a vest, and then she wore this blue jacket. And without removing this blue jacket, she is now taking off her vest. Taking of vest without taking of a coat. Since topology when your vest is outside the coat, one puts an arm to one vest coat, pulls the coat to this vest coat until it is hanging on the other arm. Then pulls the coat to the other vest coat where it is obviously outside. पता चला? Practical applications. Map of the London Underground. Since topology preserves link between them, so the representation of the two ignores the distances and the physical locations of the various stations, but preserves the links between them. The map is here. ये map है London Underground. इसमें जो distances है, they don't have a significance. It might be wrong, but the links preserve की है. और मतलब कि अगर मैं यहाँ खड़ा हूँ, मुझे यहाँ पहुँचना है, I can move from this will be always true, but distance may not be true, right? So the links will be हमेशा preserve रहते हैं, and because of this thing we can apply topology on this map, alright? समझ में आया? जैसा मैंने पहले कहा ना, if we won't consider shape, size, length, we will only see that does it preserve the properties. In this case, the links. Understood? So इसका फायदा क्या है कि we must be much clearer and that than the unwidely real life mess. Alright. Then the next one, cosmologists use a lot of topology when they are studying the structure of our universe. The exact shape of our universe has very important implications for how it began, how it behaves today, and how it might end. Researchers believe that the universe could be in the shape of a sphere, satisfying in form. Engineers put topology to work and it's very good application. The last one, engineers put topology to work helping them design robots. The movements that robots can make can be thought of as a shape in n-dimensional space, where n is the number of joints the robot has. By exploring the shapes with topology, robots can get a better idea of how the robots will move. Everyone has watched Transformers. Then other robotics movies, right? So what they do actually? Everybody has seen that movie. There is I have read the fact between the picture and when I was seeing the movie. The director said that every time that robot changes to a car, it comes back as a robot, transforms back as a robot. It will be always unique. The way will be always unique. It will never repeat that particular method. So that's the thing. But what I'm trying to say is we can also use topology in that for that usage also, right? Also for movements, if you are making a robot, but you want to check out how the movements of the robots will be acting out, then we can apply topology. We can apply animation using topology. For example, if I want to make a circle, in art I want to make circle from a square, then I will think of topology. Why? Because I only need to see that the points that are around, the points which are on the circle should remain there when I change circle to a square. Now, one branch of topology, point set topology. It is a branch of topology which studies the properties of topological spaces and structures defined on them. Invariant under homomorphism. What is the homomorphism? Not key. So basically homomorphism is what? Continuous graph, continuous map, bijection, and obviously inverse will be there as it is if you want. Right. So when I say that particular thing is equivalent to other thing, then it should mean that they both are homomorphic, right? So to compare two objects, geometric objects, check whether they are equivalent or not, we will check this condition of homomorphism. Some books also say that homotopy. We will say homomorphism because we have studied this. If one geometric object can be continuously transformed into another, then the two objects that are viewed as being topologically, this is what I say. If two objects taken like homomorphism property check करता हूँ, satisfies the property, and I will say that the both objects are topologically same or precisely equivalent, not same. The term used to describe two geometric objects that are topologically equivalent is homomorphic. This is the condition if F is the right-handed continuous constant and the inverse map also continuous, that is F is homomorphic. property should be conserved. Alright. Now, what I will see is the points on the circle should remain as they are when I apply the transformation. Alright. I apply the transformation and I say that it is a square. Is it true? Is it true? It will be, because for example consider point over here. It does remain. Alright. I will keep the center same. Right. Another thing. When I want to apply transformation over here and get back circle. Then also this property will be conserved. If I check out this point, it will be over somewhere here or here. So in short, the links or the points for the circle will remain where they are when I apply the transformation. So in that case, topologically, circle and square are same thing in R2. Space is very important. Similarly, the rectangle is homomorphic to a circle. I will write this again. Rectangle, different ways.